Okay, so now can you hear or still there is problem?
Yes, sir.
It is audible
Audible.
now.
Yes, sir.
Okay, okay. So I was telling this point, this one. Where is it? I think we are here, right? So you see, I was telling that there are two factors. Actually, what Utkarsh is asking, this there are two factors you need to multiply. One is RW1 factor, and then there is another one factor which is basically RW2, RW2 factor. So you see this RW1 and RW2 factor, instead of this RW1, you don't see any factor over here which is RW1. This RW2 factor, whatever is there, this RW2, whatever you see, this is actually W dash. So basically this RW2 is replaced by W dash. That is very clearly understood now. But where is this RW1? That you need to understand, right? So this RW1, you please try to understand here. In the Indian Standard Code, when it is giving the net ultimate bearing capacity, it is not considering the RW1 value. Instead of that, what you should be doing, you should be using this value of gamma, this value of this gamma, whatever is there, this gamma value, you need to use the exact gamma value. So if you use the exact gamma value, so gamma exact, if you use, you don't require this RW1. Now what is gamma exact, that you need to understand. So basically you see, let us see, let us say that saturated unit weight, saturated unit saturated unit weight of soil is, let's say, 18 kilonewton per meter cube. Okay, so when the saturated unit weight is 18 kilonewton per meter cube, and let's say if the water table has reached the ground level, that means what will happen. So you will have to again go back to this diagram. So if you see, if let's say this water table, this is the water table, it has reached this ground level. So if it has reached this ground level, then you see the complete portion of this soil up to this depth df, it will be under which condition? So it will be under submerged condition, because the water table already has reached the ground level. So instead of multiplying it, see, in that case, what will be your value of RW1? In that case, your RW1 value should be 0.5 ideally. So ideally what you should do, ideally if you use a RW1 factor, then RW1 factor with RW1 factor, if you go, then RW1 factor in such case will be 0.5, and your unit weight of soil is 18 kilonewton per meter cube. So how much your gamma will become in that case? So your gamma, if you use the value of RW1, then you see your gamma value will be 0.5 multiplied by 18, which will be nothing but 9, right? So 9 kilonewton per meter cube, this value you will be getting. So if you go with RW1 factor value in this case, then you will be getting 9 kilonewton per meter cube. However, if you do not use this RW1 factor over here, if you do not use RW1 factor over here, and you go with gamma exact, now what will be the value of gamma exact? As I have told you, so what will be the value of gamma exact? So gamma exact means what? Gamma exact means, let us again go back to this water table figure. So see, water table has reached here. So the soil up to this depth, that means up to the depth of the footing, this will be under what condition? This will be under submerged condition. And if you remember basics of soil mechanics, at the very initial stage you have learned from soil mechanics that what is actually your gamma submerged. So if you want to find out this gamma exact, then this gamma exact is nothing but, you see, this is going to be your gamma, this will be nothing but your gamma submerged, sub me or g submerged. So gamma exact is nothing but your gamma submerged. And this gamma submerged, if you remember, what is your gamma submerged? Gamma submerged is nothing but gamma, it is nothing but gamma saturated, right? Gamma saturated minus what? Tell me, anyone tell me, bolo, what is gamma submerged? Gamma
Unit
saturated,
weight of water.
yes, gamma saturated minus gamma W, right? So gamma W. What is gamma W? Gamma W is nothing but unit weight of water. Now unit weight of water is what? Unit weight of water is 9.81 kilonewton per meter cube. So you see gamma saturated is 18, and what is gamma W? Gamma W is 9.81. So you see how much value you will get? 18 minus 9.81. What is the value we are going to get? Tell me. What will be the value? Tell me. 18 minus 9.81 equal to 8.19, right? So you are going to get 8.19. Now you see this gamma exact value will be 8.19, isn't it? Gamma exact value will be 8.19. Instead of that, if you use RW1, what value you are getting? You are getting 9 kilonewton per meter cube. Are you getting? So this is actually you will have to do in case of using your Indian standard code. You will have to use the gamma exact value. What Indian standard code is saying? Instead of using this RW1 factor, you use the gamma exact value. But you please remember, this gamma exact value finding is very difficult. So that is why this RW1 and RW2 factors have come into picture. This gives some kind of linear interpolation thing. See, when the soil is completely submerged, then it is very easy to find out. But when the soil is not completely submerged, then you see, then what you will have to do? Suppose instead of here, water table is here. So what will happen? So in that case you observe, from here to here, that means from here to here, what will be the case? From here to here the soil will be submerged. However, if you notice, from here to here, the soil will not be submerged condition, because water table has just reached this position. So the soil below the water table, that means for this depth, if you see up to this depth, the soil is under fully submerged condition. So you can use for this portion submerged unit weight. But for this portion, what you will have to use? For this portion you will have to use saturated unit weight. So in such case what you will have to do? You will have to calculate. So let's say if this depth is d1 and if this depth is d2, then you will have to take weighted average, like the one I have explained you for calculation of phi and c. So gamma also can be calculated in such case using the weighted average value. That means this here it is gamma. So this is your gamma saturated. So gamma saturated is for depth d1. So how you will calculate? Of what it is happening? Okay, let's see. So you see what you have to do. You see gamma. So actual gamma exact, if you want to find out. So gamma exact in this case, exact. So gamma exact, if you want to find out in this case, you see how you can calculate it. Very carefully you observe. So gamma exact will be in this case, you see this depth, let's say this is d1 and this is d2, that means d1 plus d2 is equal to df. Okay, so up to this portion of soil, let us say this is saturated, and see this portion of soil is submerged. So submerged unit weight, you know, gamma submerged is nothing but gamma saturated minus gamma w. So you can calculate this gamma submerged for d2 depth, and you know this portion of soil is saturated, so this is gamma saturated. So gamma exact you can calculate in this way, you can calculate in this way, just you do it this way, that you just take weighted average, that means let's say d1 is the depth, and for d1 depth it is how much, it is the soil unit weight is gamma saturated, let us write full. So gamma saturated for d1 depth, and then for the next depth, that is this one, if this one is d2, then for d2 depth this is how much, bolo, d2 depth this is gamma submerged, yes. So gamma submerged, you know, gamma submerged is nothing but gamma saturated minus gamma w, so you calculate gamma submerged. Okay, so this is your gamma d1 gamma saturated into d2 gamma submerged, right? Now for this is happening for what depth, this is happening for the total depth, so weighted average you have taken, so d1 plus d2. So if you do this, what you are going to get, so if you do this, so see gamma exact value if you want to calculate, you are doing d1 into gamma saturated plus d2 into gamma submerged divided by d1 plus d2. Okay, so if you take this into consideration, this value, okay, so you will observe that this is a kind of using this linear interpolation, that means when you are using this rw1 as a factor for water table correction up to the depth d of the footing, then this is nearly correlating this. Okay, not exactly, but this will be nearly actually correlating this. So here to here you will be getting, okay, so this rw1 will be nearly equal to this gamma exact. So when you will be multiplying this rw1 with the gamma saturated value, you will be nearly getting this gamma exact value. Are you getting? So is it now clear, Utkarsh? So for Indian Standard Code, if you want to calculate, how will you have to take care about this gamma value? Have you understood now? Is there any more doubt? If you have, then I can explain again.
Sir,
Yes.
sir, in
Yes.
IS code, in case of general shear failure,
Yes.
the second term is written is Q NQ minus 1
Q
SQ,
NQ.
and there is no effect of water table. And in third term, it is a W dash.
Huh.
Sir, here you told we have to use gamma exact. Then
Yes.
how, sir?
Where?
In second term, Q NQ minus
That
1
is what I am
ultimate.
saying. In second term, you will have to use gamma exact value. That is what I am explaining. See, instead either you use gamma exact, or you use gamma. That means the gamma saturated multiplied by, either you use gamma exact or you use gamma multiplied by that rw1 factor. Okay. So
Okay, sir.
see I think echo is coming now. Is it okay, echo?
Yes, sir.
See what I am trying to say, I am writing it here again, you see, just on top of this I write it. Very clearly understand this one. See, can I write, I can write this equation in two way. I can write either this gamma, let us write this gamma, and multiply it with rw1. So this rw1, you see, this rw1 value is basically a linear interpolation value, right? So linear interpolation depending on the position of the water table, and this RW1 value is doing what? That is what I have shown you. See, RW1 when the water table is reaching the ground level, at that point what will be the value of your gamma? If you are trying to use the RW1 factor. So if you use RW1 factor and water table is reaching the ground level, you see your gamma value which will be multiplied with 0.5, because this is actually becoming your gamma exact, because the unit weight of soil in that case is given as 18 kilonewton per meter cube. So that is the unit weight of soil, not on the submerged condition. So if you want to take care about the submerged condition, what you'll have to do, you'll have to just multiply it with 0.5 if you use RW1 factor. But if you do not use RW1 factor, then what you'll have to do, instead of this RW1 factor, you can use this gamma exact value. So what will be the gamma exact? Gamma exact means suppose when you are testing the soil, at that time your bulk unit weight of soil or the saturated unit weight of soil is coming as 18 kilonewton per meter cube. Now if your saturated unit weight is 18 kilonewton per meter cube, this is 18 kilonewton per meter cube, and if you want to find out the gamma exact, and when the water table is reaching the ground level, at that time your gamma exact is nothing but gamma submerged, and such case gamma submerged will be given by gamma saturated minus gamma W, and this gamma submerged minus gamma saturated minus gamma W is nothing but 8.19. So one way what you can use 18 multiplied by 0.5, that is going to give this multiplied by this value as 9, or you can use this gamma exact value which will be 8.19. Now this will be true when the water table has reached the ground level, but if the water table hasn't reached the ground level, it is in between somewhere, at that time what you will do? At that time you can either use this RW1 factor with this gamma value, so that will take care about this linear interpolation, or what you should do, instead for finding out this gamma exact, what you will have to do, you will have to go back and take this into account. That means what? Your unit weight of soil, bulk unit weight of soil for this portion is gamma, right? Now for this gamma, total soil portion is gamma. Now water table is gradually rising up. Let's say at one instance water table is here and you want to find out bearing capacity. At that time what you have to do? You have to take the weighted average. That means for this portion of the soil what is the gamma, and for this portion of the soil what is the gamma. So for that, you see, we have noticed that gamma exact in that way, what will be for up to D1 depth. You see, up to D1 depth, the soil up to this depth, the soil will be in a saturated condition. Up to this depth, the soil will be under submerged condition. So what you will do? You will multiply D1 into gamma saturated, you will multiply D2 into gamma submerged, divide by D1 plus D2. So you are going to get gamma exact. Or what you can do? You can use this gamma, value of this gamma or value of this gamma saturated, and this gamma saturated you can multiply with this RW1. Now you see this RW1 when you will be using, what will be the case? See, in that case RW1 when you will be using, it will be 0.5 1 plus dW by D. So see what will be this factor becoming? In that case you will have to write this factor in this way. So dW, you see, water table, depth of water table, so dW is here, you will have to write D on, and D where you see, where we have written D is equal to D1 plus D. So both way you can do it, but Indian Standard Code is saying up to below the base of the footing you go with this interpolating formula, that is you go with the R to W value. That means below the base of the footing up to this B depth you go with this R to W formula. But above the base of the footing, instead of interpolation, you try to go with this exact formula. However, if you go with this also, you will not be wrong, to too much extent. Okay, maybe your bearing capacity will be differing by 1 to 2%, that's all. Okay, so is this clear to everyone?
Yes, sir.
Okay.
Yes, sir.
See, if you solve one problem, see whatever problem I have given now on water table, I will give another one problem. You try to solve both way. You try to solve using this weighted average formula whatever I have given, and you try to solve using this RW1 and RW2 factor. Then you will be able to understand what is exactly the difference coming for the bearing capacity value. Okay, and you will observe that value difference will not be very much. It will not be too much. Okay. Okay, so is there any other doubt? Otherwise I will just go to consolidation part. Is there any more doubt?
Sir,
Hmm.
so the assignment question you have given of circular footing.
Yes. Huh.
Sir, in that question, how we proceed to IS code? Sir, because in IS code there is nothing
Hmm.
mentioned about Q ultimate and phi of 42 degree.
IS code it is not mentioned. क्या बोल रहे हो?
Sir, sir, they have to interpolate na sir. Yet it is
Yes.
only given of phi is equal to 0, 5, 10, 50 like that.
Yes, you'll have to interpolate between 40 degree and 45 degree. So phi
Sir,
is equal to 40 degree, you have values of NC, NQ and gamma, and phi is equal to 45 degree, you have values of NC, NQ and gamma.
yes, sir.
Okay, so you interpolate between 40 and 45 degree and find out what will be the value at 42 degree. Okay.
And sir, the diameter of circular footing will be the breadth of the footing.
Yes, see, whenever there is a circular footing, see, circular footing is having only one dimension, right? It doesn't have a length, it doesn't have a breadth, it is only having diameter. Okay, so diameter of the footing will be equal to the breadth of the footing. That is the inherent assumption for any circular footing.
Okay, sir.
Okay, is it
Yes, sir.
clear? Can you solve
Yes,
now?
sir. Yes, sir.
Okay. So should I little bit start with this one? See, today's class it got disturbed for half an hour almost. So should I start with the consolidation part, 15-20 minutes?
Yes, sir.
Okay. Okay. Thank you. Let me start with consolidation part. See, I have shared one slide, right? I have shared one slide with you. So those slides, the next portions will be modified later on. Just let me start with the initial part. So let me go to that soil mechanics, then consolidation of soil. See, can you see consolidation of soil? Slide
Yes,
is
sir.
visible? Yes. Okay. See, this consolidation of soil, very important chapter. Okay, very important chapter. You must understand very carefully. Okay, but don't think that is a very difficult thing. Lot of mathematical things will come in this consolidation chapter, but first of all you need to understand the philosophy behind consolidation, and after you understand the philosophy, then you will go into the mathematical part. See, in any competitive exam, lot of questions come from this consolidation of soil. Okay, but don't think that is a very tough chapter. Okay, it's very simple. If you step by step understand, it's very simple. I will take you through step by step understanding, and then small problem solving, and then mathematical understanding about the concept. Okay, it's very simple to understand. Just very slowly we will be going, and I'll try to give you the idea. Anytime if you have any doubt, you just stop me and ask, because it's a very conceptual thing, so concepts must be clear. So let's start with consolidation of soil. I think you may have learned little about consolidation of soil in your 4th semester course. Okay. Here you will be having more detailed idea about consolidation. Now, the first thing you need to understand, what is consolidation? Basically, see, consolidation is nothing but the change in the volume of the soil. And which kind of soil? When the soil is saturated. Until the soil is not saturated, there will not be any kind of consolidation coming into soil. Okay. So any kind of saturated soil, there will be a volume change. There will be a volume change. When the pore water is expelled from the soil. Okay. So basically you see what happens. See, any kind of saturated soil, whenever there is a soil which is saturated, in that saturated soil what you get, the pore spaces of the saturated soil will be filled up with water, right? So whenever there is an external incremental load comes onto the soil, at that time what will happen, the water at first will try to take up the load, all the load, right? And later what will happen, the because of that pressure, water will try to find out a path, right? So if you put water under some pressure, you see always water tries to find some path and it tries to flow away from that place, right? So that is the nature of fluid actually. Okay. So whenever water is under some kind of pressure, it will, as the water is completely incompressible, in that way water will be fast taking all the load incrementally whatever is coming onto it. However, it will try to move away from that, means it will try to just give away the load and then go away from that structure. Okay. So in case of soil, what happens, in case of soil, between the soil spaces, pore spaces, the water is stored, right? So those water are called pore waters. Okay. Now in case of saturated soil, you can easily understand the pore spaces inside the soil will be fully filled with those water, right? And there will not be as such any air voids. So void is what? Void of void in the soil. If you think about if you remember the three phase soil system, then void is what? Void is nothing but your volume of the air and volume of the water. Okay. And the solid content is the soil content, which is the soil, only the soil solid mass. Okay. So the void spaces in that way, void spaces in a fully saturated soil will be completely filled up with the water, and those spaces between two soil particles will be filled with the water, which will be actually your pore water. Okay. So when that pore water, say anyone is trying to enter. So when this pore water will be trying to get away all the pressure and just try to move away. So at that time what will happen, the pressure will be finally coming to the soil mass, and when the soil mass will be that way coming under the pressure, the change in the volume of the soil will be happening. Okay. That phenomena will be called as consolidation. So very carefully understand it. See, the volume change, this word is very important. In saturated soil, volume change in saturated soil, this is very important. So there will be change in the volume in the saturated soil, and this change in volume will happen because of the expulsion of pore water. Expulsion means it will be going out of the soil mass. So it will be just leaving the pore spaces and it will be just going out of the soil mass. And as soon as the pore spaces are being coming empty, at that time what will happen, two soil particles will be come into contact with each other, and because of coming into contact with each other, and as the external loading is coming onto the soil, there will be change in the volume of the soil mass. And as soon as the change in volume of the soil mass will happen, what will happen, the height of the soil specimen or the height of the soil mass, whatever you are considering, that will be little decreasing, gradually decreasing. So this gradual decrease of height of the soil mass because of the expulsion of pore water pressure under some sustained loading means the external loading which is coming onto the soil mass, that phenomena will be called as consolidation. Okay, have you understood? Have you understood this? Sanjeev Kumar, who is he? Should I admit?
Yes, sir.
Yeah. So you see this way, let us try to understand this diagram now. So what is this diagram says? So it's very simple. See, this diagram says that there is a delta sigma. Delta sigma means the vertical stress. So delta sigma means delta sigma means increase in vertical stress. So let's say soil mass was under some stress. Now you are constructing a building on that. So because of the construction of the building, there will be incremental stresses coming onto the soil, and that is actually a delta sigma. Okay, so that is the vertical stress increase inside the soil. Now you see the soil, let's say you have a sandy layer, and then in between there is a clay layer, and below the clay layer again there is a sandy layer. Okay, and you see the groundwater table is somewhere here. That means you see portion of the sand is fully saturated. That means this portion of the sand is fully saturated, this portion of the sand is fully saturated, and obviously this clay is fully saturated, right? And the soil above this water table is not fully saturated. It may be in under bulk condition, or this soil is under submerged condition, this clay is also under submerged condition, this is also under submerged condition, but above this the soil may be under bulk condition or saturated condition. So you can see this clay is under complete submerged condition. Okay, and you can see because of the presence of this groundwater table, above this clay layer, all the pore spaces inside this clay, will be filled up with water, and that water will be called as pore water, right? Now when there will be increase in this delta sigma, you try to understand very clearly what will happen. Because of this increase in delta sigma, what will happen, this sand, first this pressure will come to the water, whatever is there in the sand, right? So sand, the pore spaces in the sandy soil also will be filled up with water, and the delta sigma stress will be coming to this sand. So you see that although the delta sigma pressure will be coming to the sand, as you know the permeability of sand is very high. That means the water can flow through the sandy soil very easily. So whenever there will be a stress increase, the water will be very easily able to go out of the sand because of its high permeability. So due to that reason, the pressure increase whatever will be happening inside the water or the pore water, that pressure will be termed as pore pressure. That pore pressure increase due to the vertical stress increase will be very fast dissipating. Dissipating means it will be very fast reducing. due to the reason that sand is highly permeable. However, you see, on the other hand, the clay is not that way highly permeable. Okay, the low permeability of clay will not allow the pore water to dissipate very fast, right? It will not allow the water to leave the soil mass very fast, right? So when it will not allow the water to leave this clay portion very fast, then what will happen? Then the water will have to take up this pressure, because as soon as this water, in case of sand you see, as soon as this increase in stress is coming to the water is finding some way or path inside the sandy soil to go out, move out. Okay, so because of that, the rapid dissipation is happening of the pore pressure. However, in case of clay, you see, because of the low permeability of the clay, pore water will not be able to move away or go away from the clay soil very fast. So as it cannot move away from the clay soil very fast, because of the incremental stress increase, the pore water will have to take up the initial pressure. That is the first thing you need to understand. So as soon as the pore water needs to take up the pressure, so what will happen? Because the water is highly incompressible, so high incompressibility of water will make the water to take up full this delta sigma load. So this water first hand will have to take this delta sigma load, because it cannot move out, of the clay soil, so it will have to take the full delta sigma load. Okay, so once it takes up the delta sigma load, then after, because of the low permeability, gradually the pore waters will be dissipating from the soil. So gradually it will be moving out of the pore spaces. Okay, because already the load has come onto the clay. Okay, already the load has come onto the water, so water will try to move away that stress, right? So it will always try to go from the high energy state to the low energy state, right? So to go to the low energy state, what it will try to do? It will try to dissipate that pore water pressure. And how will it dissipate the pore water pressure? Only it can dissipate if it goes away from the clay soil. And this going away from the clay soil, if you can understand, because of the low permeability of soil, the process is very slow. That is the main thing you should understand. So the consolidation process, as a process wise, if you understand, it's a very slow and time dependent process. It will not happen in a single day. Okay, however, you see, in case of sand, what will happen? In case of sand, because the sand is having high permeability, as soon as the stress increase in sand is happening, water will take up the pressure, and it will, because of the high permeability of sand, it will go away from the sand, and immediately the pressure will be transmitted to the sand, and that's how the sand will settle immediately, and that's called immediate settlement. We'll come to that later. Okay, now when the clay is having low permeability and it's not allowing the water to move away from it very fast, the water will first take up the pressure. If you go to the next slide, you will understand it very clearly. So you see, 3 steps I tried to show you in this. So very carefully you understand these 3 these 3 steps. The first one is this one, second one is this one, third one is this one. Okay, so try to understand the first one. So what is happening? So see, variation in total pore water and effective stress in clay layer. So the clay layer, whatever we have seen in the previous slide, you see how it will vary. You see, there is an increase in stress. So there is a total increase in stress. So in the depth edge, there is a total stress increase. And how much is the total stress increase? The total stress increase, because of this vertical stress, is delta sigma, right? So there is a total stress increase, which is delta sigma. Okay, now you see, at t is equal to 0, means as soon as this vertical stress is coming onto the soil, as soon as this vertical stress is coming onto the soil. So as soon as this vertical stress is coming onto the soil, it will be trying to get transmitted to this clay layer also. So how it will transmit? See, as soon as this delta sigma will come, because the clay is having low permeability and the clay is saturated, so the spaces between the clay particles which are filled with water, that means the pore spaces are filled with pore waters. So because of the incompressibility of the water, this total stress, this total delta sigma will be taken up by what? It will be taken up by this pore water. And you can observe from this diagram that pore water pressure increase will happen up to a level of delta sigma. You got it? Because water cannot move out, water cannot give any stress to the soil at this point. So initially at t is equal to 0, as soon as the vertical stress increase is happening inside the soil, there will be a state coming, where your delta sigma will be becoming equal to delta u. Have you got it? So this increase, this pore water, this pore water will take, you see, pore water takes initial change in vertical loading. That means it will become delta sigma equal to delta u, since water is incompressible. Okay. Now you see, at this time if you observe, the soil skeleton does not see any loading. Because why it will not see? Which soil skeleton will not see any loading? This clayey portion of the soil, will not see any initial loading. Why? Because the full incremental load is being now taken up by the pore water. This is the first stage of consolidation. Okay. Now you see, between time t is equal to 0 to t is equal to infinity. Okay. So basically you see, t is equal to 0 to t is equal to infinity. Why I have written it like this? Because consolidation is a very slow process and it's a very time consuming process. Okay. And it will go forever, it's very difficult to clear up all the pore spaces in between the clay layer. Because of the low permeability of clay, it is very difficult that all the pore spaces will be becoming empty from the pore water, and every soil particle will be coming to touch with each other. So that possibility will only come at an infinite time. That means it may take from t is equal to 0, let's say it may take 100 years, 200 years also. So its process is such a lengthy process. However, you will observe at a later stage, when you will be doing mathematical calculation, you will observe that maybe out of this 100 years time, the 90% or the 80% consolidation in many cases will be happening in 50 years, 55 years or 60 years time. Okay. So this may happen, but as you see, from t is equal to 0, this years time we are taking, that is actually your infinite time. Okay. So this infinite time, when you are thinking, you see, at this time what is happening? This with pore water increase, the pore water increase due to initial loading dissipates. Okay. So pore water increase due to initial loading dissipates. That means what is happening? See, initially it was delta sigma over here. Now you see, delta u was delta sigma. Now what it will start? Gradually, pore water will try to dissipate from the soil. Dissipate means it will try to move away from the soil. Okay. So when it will move away from the soil, what it will do? it will release its stress, and who will take up that stress? The soil mass will be taking up that stress. So you see, this case will prevail. So with this pore water, so between t is equal to 0 to t is equal to infinite, you will see that soil skeleton will start taking the load as pore water pressure decreases, because pore water pressure will decrease with the movement of the pore water from the soil. Because of very low permeability of the clay, this process is very slow and very much time consuming. Okay, you may not be able to see it in 1 day, 2 day, 3 days. Okay, it may be taking years together. That's what I am saying. Okay, so when this delta u, you see delta u will be gradually reducing. In that case, what will happen? The soil mass will start taking up the stress, and you see the effective stress in the soil will be increasing. That means what is happening? This clay layer, initially this delta sigma was completely taken by the water present in this clay. Later what is happening? This delta u, this delta sigma, this delta u is just going away. That means the delta sigma part, portion of this delta sigma part will be taken up by the soil mass. And when the soil mass will be taking up this delta sigma part, you can understand now very easily that when it is taking up this delta sigma part, it takes lot of time to take up that delta sigma part, because the water, unless and until the water is moving out of these pore spaces, it will not leave any stress into the soil. So when it will start leaving that stress into the soil, at that time water, the effective stress in the soil mass will start increasing. So this way, one diagram you see it is coming down like this, and one diagram you see it will be increasing in this way, in this direction. Okay, along the depth direction. So basically you see this blue, this portion, first case, at first time soil skeleton does not take any load. Full load is being taken by the pore water. Now between t is equal to 0 to t is equal to infinity, you see gradually pore water is getting dissipated, and that means pore water is leaving its stress, and who will be taking it up? The soil skeleton will be taking the load. Okay, so this is the second case. And the third one is at t is equal to infinity. That means when this complete process will be over, and at the time when the complete process will be over, then what will happen? And that will come in years to come. Okay, not in 1 day, 2 day or 3 days or 1 hour, 2 hour. Okay, so when the complete pore water pressure will be dissipated, at that time what will happen? That delta sigma, which was initially, you see, initially this delta sigma was completely taken up by this delta u. Now you see in the third diagram, at t is equal to infinity, what is happening? This complete delta sigma, this complete delta u has become equal to 0, which was initially delta u is equal to delta sigma. That means the pore water pressure has been dissipated completely. And when it will happen? This dissipation of pore water pressure will be happening completely at t is equal to infinite. Okay, and when this dissipation of the pore water pressure will be completely happening, at that time what will happen? You see, the total pressure increase, this delta sigma, whatever is the increase in the stress, this vertical increase in the stress, who will be taking it up then? This clay, the effective stress in the clay will be completely getting increased by this amount delta sigma. So this delta sigma is the increase in the stress from the external loading, and this delta sigma will be now completely taken up by the soil mass. So that is actually your effective stress increase. So you see, at t is equal to infinite, what will happen? The pore water increase due to initial loading completely dissipated. So what does it mean? Initial loading completely dissipated means initial loading is nothing but your delta U is equal to delta sigma. So when the initial loading is completely dissipated from the pore water pore water, then your delta U will become equal to 0, and finally the delta sigma part will be completely taken up by the soil skeleton. So the effective stress increase in the soil will be equal to this delta sigma, and that will be equal to delta sigma equal to delta dash sigma, or delta sigma dash. It should be delta sigma dash. Okay, so is this clear? So this is actually the process of consolidation. If you understand it very clearly, then only we can proceed further. Is there any doubt on this?
No, sir.
No. Okay, very good. I will take up another one slide. Okay, then we will stop today, and in the next class we will discuss further. So you see, in the next slide, this model is very commonly used to understand the fundamentals of consolidation. You see this, it's a very simple model. Okay, it's called the spring analogy. So this spring analogy explains the consolidation concept very easily. You see, what is this very simple concept? You see, a a a a a can sorry a can is there, and that is a that is filled up with water, you see, and the water, and this is blocked from this side, you see, this is also blocked, and there is a spring. You notice this is a spring. Okay, now you put a weight on this, what will happen? As you put this weight on this, as you put this weight on this weight will try to press this spring, right? This weight will try to press this spring, but you see, initially you will observe this spring will not be pressed at all. Why it will not be pressed at all? Because of the incompressibility of the water. You see, because of this incompressibility of water will be taking up this full load of W. Okay, so initial loading, when it will happen, you see, water takes the load, that is soil. So you see, if you see the soil, this can be considered as soil. This complete thing can be considered as soil mass, total soil mass. So that means soil is which one? Soil in this case is spring. So in the spring analogy, if you understand, this soil is nothing but this spring, because finally who will be compressing? What will be compressing? The soil will be compressing, and this water, whatever is filled in this tank or this can, this is actually nothing but your pore water. Okay, and this W whatever you see, this is nothing but your increase in the vertical stress, that is the delta sigma we are talking about. So initially when you are putting this weight on this, you see, if this water is not allowed to move away anywhere, then full load of this W will be taken up by this water. So the water will be taking the full load, and you see the soil, which is basically the spring, which is modeled as the soil, it will not have any load. So this first condition, that is at t is equal to 0, the condition in the previous case whatever we have seen, this at t is equal to 0, delta sigma is equal to delta U, that can be explained by this spring analogy model. So you understand? So this spring is your soil, and this water is considered as pore water. Okay, and you see, this is blocked to move. So when the weight is coming, see, this water cannot move away anywhere. So the complete load at t is equal to 0 is being taken up by the water. So when the complete load will be taken up by the water, the increase in the pressure in the water, that is delta U, will be equal to the pressure which will be created by this load W. So delta sigma is equal to delta U. Now this is the case B. So case B means from t is equal to 0 to t is equal to infinity. So what will happen? Let's see. So that's what you have seen. See what you are doing. Now you are removing this cap. So as soon as you remove this cap, what will happen? This water will spill out from this. So this spilling out of water is basically dissipation of the excess water pressure, because water is under tremendous stress or tremendous pressure at this condition, right? Now you observe here, if you make this hole bigger, this dissipation will be much faster. So you can compare the permeability very well using this model. So if you make this outlet very small, then you see very small amount of water will be able to come out, right? So very slowly the water will come out, and if very slowly it comes out, that means it will continue up to infinite period to move away this total water from this tank, right? But if you have a bigger kind of thing, bigger kind of hole over here, then very fast it will go out, and that's what it is happening for sand, right? In case of sand, which is highly permeable, if you see, as soon as the water takes the load, because of the permeability, that means if this hole is much bigger over here, then very fast this water will go out of this tank, right? And complete load will be taken up by this spring. So that is actually happening to sand. But in case of clay soil, if this outlet if this opening is very small, that means which is actually depicting the low permeability of clay, in that case what will happen? Very slowly you see this water will go out of this tank, and when this water will go out, you see this spring will be getting folded. See, in this case spring was like this, you see spring starts taking the load and it is getting folded, right? So what is happening, you see dissipation of excess water pressure is happening. So dissipation of water pressure means what? This delta U is becoming lesser than delta sigma. That means gradually water is leaving its trace, because it is going out and it is giving it to the spring. Okay, so dissipation of excess pore water pressure is happening. So water is dissipating. So this is actually dissipating of water, and the soil starts to take load. What is the soil here? The spring is the soil over here, and the spring starts taking the load. So basically the soil starts taking the load. Okay, now at t is equal to infinite, what is happening at t is equal to infinite? So I told you that it's very difficult to reach that t is equal to infinite, and you don't know what is that infinite period, because it's very difficult to move away all the water from the soil. So you see still some water is being left in this tank. So that at the final loading stage, you see water dissipated. See, all the water must be dissipated at t is equal to infinite, but it's very difficult to dissipate. So some water will be remaining. So it's very difficult to reach this state actually. So it's very difficult to reach the state delta U is equal to 0. Some delta U will be remaining, and there will be some amount of stress will be taken up by the pore water, which is not able to go away from the soil mass because of its low permeability. And finally you see, if you can reach a state when the complete water can be expelled out, or complete water can be moved out from this can because of this load, then you see this spring will be completely compressed, and at that time the soil will have the complete loading and the water will be completely dissipated. So your pore water pressure or the excess pore water pressure will be completely dissipated, and that time your delta U will become equal to 0, and your delta sigma will become equal to delta sigma dash. Is it clear? So if you remember this spring analogy, it's very good to understand consolidation. You can remember this, and if you remember this, your consolidation concept will be always clear. Very simple to understand using this spring analogy concept. Okay, so I think we stop here today. Okay, so is it clear to everyone? Have you understood?
Yes, sir.
Yes, sir.
Okay, so let me take the attendance, then we'll stop. Susanto Das. So should I admit him?
Yes, sir.
He was there in
Yes.
the class. Don't know. Let me take the attendance, then we'll leave. Just a minute. Just give me some time. Google Meet attendance. Refresh. Refresh it. 25 people. Google attendance collector. Download. Okay. I've taken the attendance. No problem. Okay. So if you have any question, you can ask, or we can stop now. Okay. So should I stop?
Yes, sir.
Yes, sir.
Okay. Okay. Thank you. See you in the next week. Okay.
Thank you,
Okay,
sir.
sir.
Thank you. Okay, Utkarsh is there. Utkarsh or left?